the truncation parameter capital N such that the norm of un of t in Hs, no, the time derivative, sorry, of this Hs norm is less than constant times the N-infinity norm of the gradient of un times the Hs norm of un squared. Okay.
So we have square. So we have square on the left hand side.
I have a square here and I have a square there. So square here and there. Okay, so I have this inequality with a constant here which is independent of capital F. Okay, and from there we can deduce the following uniform bound for S greater than d over 2 plus 1. You can find some time Ts and some constant ms such that the Hs norm of un is less than ms for any t less than ts. Okay, so from this crucial estimate, you can tell that for S large enough to find always its critical index, the Hs norm is uniformly bounded. Okay. The Hs norm is uniformly bounded. That's the uniform bound I was looking for. Right. So let me explain to you how you prove this. So, look at the proposition. For S equals 0, we already made the computation. Okay, for S equals 0, it's even much better than that. We have the d over dt, which is 0. Of course, things get more complicated when you take derivatives. So what should you do? You take some alpha, some number of derivatives with alpha less than s. What you want is a control of d alpha un in L2. If you have a control on d alpha un in L2, then for any alpha like this, you will have a control of the Hs norm. So how do you get a control of these derivatives of un? You look at the equation satisfied by this guy. So you take, you apply d alpha to the Euler equation, or to the equation in En. Your approximation. So what happens when you apply d alpha? You get that dt of d alpha un plus p of the plus chi n of d p d alpha of un dot grad un is 0. This derivative, it commutes with the frequency truncation, it commutes with the lower projectile. Now, you see I have this derivative of this quadratic term. So, you know, it's Leibniz rule. I will distribute the derivatives over the two terms. Okay? And in this, I will isolate, I will single out one term when the d alpha goes over this guy. Okay, so I will write it as dt of d alpha un plus chi n of d p un dot grad d alpha un and I will put in the source term all the other terms that you get when expanding this product. Okay, so all these other terms will be chi n of d p and the commutator between multiplication by un and the derivative. So what is this that maybe you don't know? When I denote AB like this, the bracket of A and B is the commutator. That's AB minus BA. So basically, I apply Leibniz rule and I single out one term on the left and I put all the other terms on the right. Why did I single out this guy? Because you see, I want to control over this quantity. D alpha un, that's alpha derivatives. But here I already have a gradient and I have this alpha derivative. So it's alpha plus 1 derivative here. So I have to do something special with this term because I will never be able to have a closed equation on this guy if there are more derivatives on that guy. So this guy should be somehow disappear. Okay? Or we have to do something special for this guy. Whereas for the other guys here, I subtracted the worst case. So here, I never have more than alpha derivatives on one guy. So how can we handle this? Again, this is thanks to the nice cancellation that we have seen several times. So when I multiply by d alpha un and integrate over RD, what you get is 1/2 of d over dt of the n2 norm squared of d alpha un I let you check that this goes away. So you obtain the integral over Rd of un dot grad d alpha un times d alpha un. And this guy at the right hand side, so I multiply by d alpha un, so I can make Cauchy-Schwarz inequality, so that's less than commutator of un and d alpha dot grad un in L2 d alpha un in L2. Maybe I'm a bit quick, but you can check that. So this guy here, that's the special term, and you have this nice structure, un dot grad f times f. And we have seen that when you integrate these kind of things, it goes away. So this is 0. So this bad term disappears from the estimate. Right? And you are left with all other terms coming from the expansion of the derivation. And this you need to estimate, right? So the problem now is to estimate the right hand side. And so, to estimate this right hand side, the key point is the following commutator estimate. What happens when you look at, so how is it?